Right? So, yeah. Um, I could see my white screen there. My white
Yes,
guest.
sir.
I can fit everything in place. I forgot I didn't make some notes available to you. Um, I just went into Moodle and we were talking. I realized I didn't make any notes available. You have to read up in advance. So we're going to look at circular motion, right? Motion in a circle, motion in a circle. We are going to concentrate on form, circular motion, right? And by this I mean there's an ideal motion. I think this is the word here we're going to concentrate on. We're basically going to talk about body going around in a circle, but at constant speed, right? A constant speed. And later on in the discussion, you see why I use the word speed and not velocity. Because this is a very good example to bring out the difference between these two, right? When you talk about circular motion, body might be going around at a constant speed, but guess what? It is not at a constant velocity. Anybody can say why? So this body, okay, there's a body here going around, going around, going around. And it's moving at a constant speed. Maybe let's give it a number. 10 meters per second, constant going around. Why is the velocity will changing? Any thoughts? I could we say, and I'm giving you half the answer there. Why can we say that the velocity is changing? Anybody is with me? Or people just turn on their computer and run or cook and so on. Think of the definition of velocity. Think of the definition of speed. And look what's happening as you go around the circle. What's happening as you go around the circle? Think of direction, okay? The thing might be okay, going this
So the
way.
direction changes.
That's it, right? The direction is
Yes,
constantly
sir.
changing. So even though it's moving at this constant speed, this is the speed here, right? The velocity is changing because velocity is made up of speed and direction. So the fact that the direction is changing, right? And this is an interesting thing now, right? Here it's not a number 10 that is changing. That's constant. It's moving at a constant speed, but the direction is changing. And therefore, one would argue that the velocity then is changing. Right? So it's moving at 10 all the time, 10 meters per second, constant speed. But because it's changing direction, then it is changing velocity. And when something is changing velocity, we're just doing an overview here. I'm going to go back to the nitty-gritty and define formulas and so just now. But just so you get the overall idea of what's happening in circular motion. So if something's velocity is changing, what would you say about that body? If the velocity, changing velocity means what? Means what? What is the body doing if it's changing velocity?
Sorry, the body is moving.
Well, what kind of mediocre answer is that, man? Think of, okay, yeah, the body is moving. We talk about circular motion. Everything is moving. In this topic, nothing is at stationary position, right? Everything is moving. But think of the word, think of this phrase. When the velocity is changing, what's happening? What is the body doing? Think back of motion in a straight line. Hmm. So something starts at U and it ends up at V and it takes time T. What's happening here? What is it doing? How does it move from U to V in a certain time? What is it doing?
Or is it accelerating?
Yes, it's accelerating. Changing velocity means acceleration, right? So the body is accelerating, right? So even though, keep this in mind, here is a body moving at a constant speed, and yet it's accelerating. It seems to go contrary to all that we were doing. But circular motion, well, that is what's happening. Constant speed, yet velocity is changing. Why? Because as the body goes around in a circle, it changes direction, right? We switch over now to the velocity is changing. Because if direction is changing, well, then the body is accelerating. Let me go a little further now. Let me go a little further. Newton's law, second law in particular, says that for acceleration to take place, what must you have? What must you have? Newton's second law. Hmm? For acceleration to take place, you must have a what? What causes acceleration?
Sorry, the force.
Yes, F equal ma, yeah, right? You have for acceleration, you need a force, right? And therefore, to keep a body, let me just move it over there. To keep a body going in a circle, you have to have a force, right? And now we're going to learn, well, you get all of it plus now the mathematics, right? We're just talking theory here, right? We're kind of examining what happens as our body goes along a circle. So let's say the body is initially going in that direction. I mean, if it's going at a constant speed, the body will tend to go straight out there, but something is pulling it, and then to keep it in the circle, and then it goes like that, right? Well, I mean, it's not going off there, but something has to pull it. I have to project the arrow to kind of show the direction the body would have. But because there's a constant force, right? There's a force pulling the body. It's going to go like this, then go like that, then go like that, then go like that, then go like that, you know? There's always a force, and that force is what is creating, right? That change of direction, so that it can move, it can go in a circle. See, so that's what the force does. It's going on, the body might be going at constant speed, but the direction is changing. And the reason why the direction is changing, right, is because there's some force. And then we learn later on that the force will be pulling in here. The force will actually be pulling in here. That's why this thing, instead of going off at a tangent, it kind of go this way. And when it's here, we pull again, You know, pulling again, the thing goes this way, right? And then you pull again, right? And the thing goes this way, and so on and so on, right? So, and we learn the name of the force in just a moment, right? I don't know if y'all, as kids, y'all used to do this. We used to take what you call paint can, right? When we were little, take a paint can, pull it with water, and we tie it on to a rope, and we would swing this paint can, you know, we swing the paint can, they're almost like that. And we would tie a rope here and swing this paint can right the way around. Guess what? The water in here don't follow. The water in here, right? You want to learn about something called centripetal. Centripetal. We'll hear about centrifugal forces, right? Yeah. So just to give you an idea there, you know, what's going on when a body is moving in a circle, you know. As we said, we're going to concentrate on the simplest of circular motion, right? And that has to be motion that is that has a constant speed. We're not dealing with variable speed because that complicates things. And we're going to try to stick to, let me see what we can talk about. We're going to talk about, like, okay, something moving on a circle on like a horizontal circle, right? The body is moving on a circle, right? In a circle, or if I'm to look above, from above, it's just going like that, right? You can have a body moving in a horizontal circle with a string attached here, right? You're swinging within a circle, right? I don't know if you all ever do this with something. So it's a horizontal circle, but the string that is keeping the body going is actually at an angle to the horizontal, right? We're going to deal mostly with horizontal circle, right? We are going to deal a little bit with when a body is on a banked track, you call it. It's going to go almost in a horizontal circle, but the track is banked, right? So it's not horizontal like this, but it's banked. But if you were to look at it from the top, it's like the body is going around in a horizontal circle. Those are the very simple situations we're going to look at, right? But before we get into all of that, you have to talk about some very basic quantities when it comes to circular motion, right? And one of the first quantity we'll have to deal with is the quantity called angular velocity. Angular velocity, right? So, okay, let's take a body going around in a circle, right? So if the body is to sweep out an angle of, okay, moving from here to here, you know, A to B, and it sweeps through an angle of theta, and it takes t seconds to do it. Then we say that angular velocity, this is the fancy, uh, this is the fancy symbol we'll use, right? So angular velocity is going to be equal to theta over t, right? Theta over t. So this is you never use it so much, but you need to kind of be introduced to a velocity that it's not linear anymore. It's angular, right? It's the angle swept out divided by time taken. Just like you have, okay, distance traveled over time taken. And what we can relate this. We can relate this. Let me see if I can look at this diagram. See, we can kind of Yeah, I think so. We can connect the two, right? Okay. All right. So what's this distance here? Let's say this distance from this distance back, right? Okay. Call this R. So that distance is R theta and over time, right? So that would be the, what do you call it? What is it? The linear velocity, right? No, sorry, the linear speed. Let me go with the speed, right? I'm going to use V even though, yeah, I'm going to use V even though you can argue with that, right? So if I'm going to take that, right? Speed being equal to uh, R theta over T, right? So I'm thinking what we can do. If we take theta, would that equal um, linear velocity? Right. I will put this in the place of that. What do you have? This time, okay, R, so that R over the time. So these two will move. So that V equal, um, I'm trying to remember what Greek letter this is. So can somebody Google this letter for me? Greek letter. I think I'm slipping. So we do see a connection here, right? While somebody's Googling what Greek letter that is. It's angular velocity, what's happening? So we do see a connection there between V, which is the linear speed, and the angular velocity, right? There is a connection. That's not bad. Anybody doing it for me? But I gotta do everything in the class. I'm like the pot boy, check the pattern from back. Anybody Googling it? So what we're gonna do now, um, we can actually adapt, those linear, what we call motion in a straight line formulas, where the acceleration is constant, because remember we're dealing with a circular motion, where the linear speed there, the linear speed is constant. The linear speed is constant. Therefore, the angular acceleration, which I use alpha for, is going to be equal to, I'm asking for, I can't remember this symbol, minus, what is this, omega over t, right? And from this, I'm not going to do all the steps, right? From this, we can actually get a whole set of, equations, right? So angular uh, velocity is equals to initial angular velocity, omega, plus alpha t, right? That's just like v equal u plus at, right? And there are some others, remember theta, that's the distance, the angular, or the angle swept down. There's a formula like that, I think it's half plus this times t. Anybody find out what this symbol is? Go over here for the other one like this. So you get, S is equals to ut plus half at squared. Remember that one? Another one. S is equals to vt. There's angular speed, the final speed, that is minus half of t squared. Anybody check anything for me? Here the last one. There will be square minus v square plus 2as and all that thing. Huh?
Yes, sir. The letter is it's omega. It's a common one.
Oh, that's common omega. That W thing, right?
Yes, sir.
Oh, great. Who's talking there? That's a strange voice.
Sirat, sir.
Oh, great. So those are some equations that you can actually use, right? In solving problems involving a body going around in a circle. Good. Well, maybe you're writing. I don't know if you're right. You got that? You got those already?
Yes, sir.
Huh. You said yes? Can I move it?
Yes, sir.
Yes, sir.
All right, great. Yeah. Uh, good. Very good. I think. Good. So, if you look back at your notes now, um, the notes I sent to you, you can look at the motion a different way. And if this body is going around, it's going around a circle, it completes a circle in a certain amount of time, right? And the velocity is 2 pi r. This is the distance traveled over the time taken, right? The velocity will be that, right? I shouldn't use the word. I think I'm using the word wrong. This is not velocity, but speed. The speed, because the thing is changing the velocity at every point on the circle. Yeah, I am recording this thing, so when people hear it back, I said it by like the same thing like that. Yeah. Well, I follow y'all, y'all make me feel sleepy. Back in shifts, chipping. Yeah. So if you treat it like that, right? The speed, right? Kind of speed that the body is moving around the circle, the entire circumference over the time that it takes to cover that distance, right? So that's one. Now, you probably remember we were talking about it. Well, what is it that is changing the direction as the body goes around the circle? Well, there's a force. There's a force, right? That is creating that, or instead of the body moving up at a tangent. Because again, you remember that little bucket, that little paint can illustration I was talking about, putting it in water, spinning around. There are times when the rope, sometimes you pick up some old ropes like that, and some old, what we call chalk line twine, and the thing would cut, and guess what? The bucket would actually kind of go off at a tangent, knock somebody. What's preventing that from happening is a force that is pulling. So when this thing, instead of it moving off at a tangent, force is pulling it back in, right? So when it comes here, instead of going up at a tangent, the force is pulling it to keep it on the curve, right? And it's pulling that way. Right? And that force is called, we said, is the centripetal force. Centripetal force, right? And that force creates a centripetal acceleration as well, right? And I think there's a relationship. The acceleration v squared over r, right? V squared over r. Here's a we just found the relationship between omega and v, right? We just found a relationship between the two, because I think he said, did he say that v is equals to r omega? Did he say that? Somewhere that side? Right?
Yes, sir.
So if we were to put r omega here, right? Here, we should get the acceleration is also r omega squared. Right? See the front. I think you'll agree there, right? And the force, remember we said you need a force to do it. So the force is going to be equal to mv, if you want to put mv squared over r, right? Right, because remember f equal ma, and a, m times the a will give you this, or also if you want to write it as m r squared, right? Got it? We can take this, move this out.
Yes, sir.
So maybe we can look at a couple of examples. I'm looking at one here that's let me cut the one that all right, so here is the some kind of model airplane, a plating thing, and it's being spun around in a circle. It's parallel to the ground, so we're dealing with a horizontal circle, right? And you want to find the tension in the guideline. So they're talking about a little, maybe you tie on a string on your spin, right? So you want to find the tension, right? So let me give you the diagram that we have. Right, so it's the diagram that we have. You can see it, right? So some guys,
Yes, sir.
and is playing to some kind of thing recording attention, you know? I want to know, well, what will that little gadget that he has attached to it, what will be its reading, right? So simply make use of the formula. What's it? F equal, well, that's the tension, right? The tension, that's the force that is keeping the plane in that circle. mv square over r, you substitute. And they talk about two different speeds, so cut it there. Yeah. So you just substitute the values inside there. You know M, you know V, you know R. And when it's moving at 90 meters per second, that's the tension. When it's moving at 38 meters per second, that's the tension. That was the red, right? So we're making use of the formula F equal mv squared over R. Get it? Let's take this next one. This is a nice one. For guys going along a turn, you know, especially when, and here the situation is, the situation is, you're assuming like a horizontal road, right? So you're going along maybe a core. Notice they say that the place is horizontal, it's unbanked. You're going to understand our word unbanked just now because we're going to do what we call bank track, right? We'll do that in a minute. Good. So you want to know at what maximum speed can a car turn safely, right? A turn, the radius is 51 meters. Right? Well, we're talking about two situations. In dry weather, the coefficient of friction is equal to 0.95. And in icy weather, the coefficient is a lot less, right? And little, I mean, most of you are drivers in the class, right? You realize that when you're going around the turn, can I ask you, what is it that keeps that car from running off at a tangent? You're going banking a turn, banking a turn. If you see you, man, you heading this way, and if let's just say you're kind of banking the turn, what's keeping you really going around in a circle here? And from the tire from skidding?
Sir, friction?
Yeah, it's a friction between the tire and the road and nothing more. Because the engine is what is creating the thrust forward. right? That is what is pushing car forward. That is what is pushing car forward. But what's keeping the car? And you just feel it sometimes, right? I have a torn here, Palmera torn. We have seatbelt torn where I live here. You can feel that you're moving to one side of the seat as you go around the torrents. And what's keeping the car from what's happening to me? From going off the edge? Oh my, give me a second.
The outer portion of the road is a bit higher.
No, in this case, notice the road is horizontal. Right? The Palmyra torn and the Sewell torn, they are banked. They are banked. Banked means there's a little slant, right? You can go to that just now. But if the road is actually flat, right? It's the frictional force of the tire, or else the car they don't fly off the edge, right? So you're using these formulas, and remember this frictional force is actually mu times the normal force, right? Which is the weight of the car. So it's good for the car to be heavy too, right? Good for the car to be heavy, and you want mu to be very high, right? So you know that this now, we got this already. Mu was 0.95 in one case and then 0.1 in the other case. The normal force is going to be the weight of the car, right? They have a weight, they don't have a weight. All right, let's go with mg, right? Let's go with mg. Because I think the m is going to cancel. You know g, we can probably use g as 10 or something, right? So let's put that in the formula. Let's put that in the formula. So let's take when it's dry weather, 0.95 mg is equals to mv squared over, what was it? 51? 51 was it? So this,
Yes, sir. 51.
that thing. And p then will be 0.95. Let's use g as 10 times 51, all divided by 1. Oh, you don't have to find the square root of that. And you get what?
Sir.
What do you get?
22.
22? Yeah. And in IC weather, if you were to put mu was 0.1 here, 0.1, you get v equal 0.9, oh, sorry, 0.1 multiplied by 10 multiplied by 51, and you will get what?
Seven point one.
10?
7.14.
7.14.
Yeah, roughly 7, right? So you see what they're telling you? When you see the road dry, yeah, you can try the passage storms. But when the road wet, you should only be going, what, 7 meters per second? Let's change this to PM per hour. This is meter per second, right? change it to PM per hour, and then you'll know how slow you need to be driving, right? One thing I like when rain falls, I don't speed really, right? But what I like about rain when rain falls, there are no pedestrians on the road, all they going on highway. There are no motorbikes on the road because all they going on highway, right? So I like that. Yeah, I noticed that with night driving as well, you know. A lot of pedestrians gone home. Um, a lot of people are home, you know. So you have the whole road to yourself. The guys who when I was, you know, learning, and somebody said, "Why you got to care for a rainfall? You got to care for it at night." I realized those are the best times to drive. Of course, yeah, crazies that are drunk, they're more in the night too, right? Well, so you had a little exposure there to, you know, something moving in a circle. Um, let's take maybe another one. Let's take one. Oh, I'm seeing here got some. Look at this. So you have the last example will be with this one, right? So you got some object here. You got some object, and you are kind of spinning it in a circle, right? With a string. And let's say the string is 2 meters. R. I know R. Let me go with this here. I'm borrowing a problem breakup. So the weight of this object is 3 G-newtons. Down here is 1 Newton. I want to keep that thing moving in a horizontal surface, right? You ever done something like this with maybe a little object on a string? I take off my spectacles like a gun, completely blind. I can't see anything. Oh shoot. That's why I make this up. Yeah. So they want you to find omega and tension in string, like this T here, this tension. Tension in string on omega. So what would you do there? Any ideas what you can do there? Would you perhaps find, because this force that you are putting up here is actually, it has a component this way, right? And so T, what would this be? Let's call this alpha, right? Or so, yes, alpha. So this will be T cos alpha, right? So we need to find alpha. Can somebody find alpha for us? Using those numbers there, you got the opposite and the I'm thinking also if I resolve it this way, T sine alpha. So T sine alpha is going to be equal to 3G, right? Is that so? If we were to look vertically, so vertically, T sine alpha equal 3G. And if I could do this horizontally, T cos alpha is equals to, what's that? M, oh, we got M, right? We got that's 3 V squared. No, let's use that one with omega. 3 R omega squared, right? So could we find all of these things what they want? They want omega and they want T. So maybe we can find T here first, no? Can we? We gotta find alpha first. Anybody found alpha?
30 degrees, sir.
30 or 16? How much you say? 60?
So it's 60 is 1 meter divided by 2, and you find the inverse. It's 60.
60 degrees. 60 degrees, right? To be honest, I was going to tell you that because the formulas connected to circular motion are really, I mean, it wouldn't affect our calculation here, but usually you have to write these in terms of radians, right? Because the formulas derived for circular motion made use of calculus, right? So you're not supposed to be working in degrees. So we got the angle. So can we now find T? We can find T. Can we find R2 using Pythagoras theorem? We can find R here. We can find T from this, because we know 3G, you can use G as. We're going to use G, you can just. Sine of alpha is that 1/2 equal half, right? So half T is equal to 3G. So T equals 6G. That's all. We get one thing here already. We got the tension, right? When we find R using Pythagoras theorem, what would it be? Square root of 4 minus 1. Root 3? Root 3? So what do we got? Oh, that makes sense. So we got 6G. But oh, we know cos alpha. Cos alpha is going to be root 3/2 is equal to 3. What's R? R is root 3 omega squared, right? So what can we do? This will cancel with that. Two will cancel with 3 of this. And then this 3 and this 3 will cancel. And what are we going to have? G is equal to omega squared. So omega equal to root G. Huh? Follow that? The circular motion problem became a trigonometry problem. I can move this out. You see it, you know. Good. So let's talk about that bank track stone, right? Let's talk about that bank track, and I like this diagram they have in the notes here, right? So when you have a bank track, like the Palmyra and the Seawell tone, something like this is happening. That's what the bank track look like, right? A little, what's which one talking about it? The road is kind of slanted, right? So they have like the outer part is kind of high, and the lower part or the inner part is kind of low, right? Now, the reason why they do this, there's a little bit of science here. Let me touch the diagram that we have after here. So when you do that, this is what happens. So you will find that there's a component of the weight, right? Notice that, okay, the weight acts this way, that force acts that way, right? And well, okay, acting this way would have been what? Mg for this angle,
MG cos theta.
yeah, cos theta, right? And then that would make this angle here, this here, sorry, this force here, equal to that. So the whole idea is that there's some force, a component of Fn, right? If Fn is this here, you break it up into two parts, right? Right here, got Fn cos theta, and down here is Fn sin theta, right? And that force is going to actually be pulling, helping the car to stay on the curve rather than run off, right? And run off the wheel, right? So when we put that in the formula, let me cut that down. Let me put that in the formula. Yeah. When we put that in the formula, Fn sin theta is what is keeping the car from, flying off the road. Fn sin theta equals mv squared r, right? And we're going to do the piece thing. Right. We're going to take this here and this thing here, man. Yeah, good. So notice here, Well, remember my good friend, what's his name? I have to bring down this way. So, so, so mg is equals to fn cos theta, right? So if you were to divide throughout by that, you were to divide through, look at what happens. These two cancel, you get tan theta. M and the M will cancel, you get v squared over rg. And this formula can now give you like a short or a fast way of figuring out, well, I mean, every track would have a certain angle. You know the radius maybe, right? And you can now tell what would be the speed limit that you should be going at, right, along that bank track, right? I mean, if your tires too, remember this does not factor in. This does not factor in the friction of the tire. That can get a little more complicated, but it does help. The tire does help, right? Here we're talking about just the weight of the car kind of pulling you in, right? So you don't fly off the road. So even though this formula will give you a certain V, you can probably play around with a little more speed, a little more, not much more, where the tire is going to help you a little. So if you do a calculation and you figure out that V is a certain value, maybe you can do a little more because the tire is going to help you a little too, right? But don't count on it. You see, there's a problem. Yeah, I think so. What do you have one there? Something about the Daytona. That kind of racing thing there. Right? Look at this one. Right? So they give you everything. So they want to know, okay, they give you the radius of the track. They give you the angle that the track is banked. Right? And you notice they're telling you that the wheel doesn't help. Right? They're telling you, forget the wheels. They say, suppose these maximum radius turns were frictionless, right? Meaning that the tire isn't helping you at all. At what speed would the cars have to travel along it, right? So you just, what was the formula we just had? Anybody remember it? You got tan theta. You put in the numbers here. Tan of 31 degrees equal to v squared over 316 multiplied by, let's go with, so I want to go 10 or 9.8. Right? So v will be the square root of 316 by 10 by tan for the 1 degree. Somebody tell me how much is that? I think they have it here. Oh, they use 9.8. And they got 43 meters per second or 96 miles per hour. Right? That's not much. That's not nice. So this is a little note at the bottom, right? Here it says. It says drivers actually negotiate the turns at speeds up to 195 miles per hour. How come they can do that? If the bank track tells them they should only be driving at this, how come they're doing what? 195? Where the extra force is coming from that helps them to stay on track? Huh? I actually told you that, right, before?
Yes, sir. Friction.
Where, what kind of friction? What friction? Hmm.
From the tire.
Hey, Orwell, remind, remind me to give you an extra point for that. Yeah, the tire. Yeah, man, wheel Brad, sir. Right? Yes, the tire has to help them. Imagine,
Yes, sir. I was about to say that.
yeah, the actual tire is helping more than the banking of the road. Just imagine that. Right? Because they're supposed to be doing roughly 95. They're doing 195. The 100 more miles per hour was helping them is the what do you call it? Is the friction between the tire and the ground. Even though the problem did say here that those turns are frictionless, that's not, that's not true. There must be some friction, right? So it's interesting. Yeah, it's all in the notes. So I can do some reading. And okay, I can move this.
Yes, sir.
Good. So lastly, we want to just talk about satellites in orbit. Satellites in orbit, right? And all of you would know that really, you all know that when they launch a satellite from the Earth, right? This is the Earth today. And they launch a satellite, shoot up a satellite. And it kind of goes round and round. Oh gosh, don't go farther. It will go round and round forever. Do you know that? It goes round and round. It will go round and round forever. It doesn't
Yes,
have
sir.
will to do that too, right? It's the force, the centripetal force that is produced by the Earth, the gravitational pull of the Earth is going to keep that thing going round and round and round and round and round and round forever, right? The only reason they'll probably make a satellite come back to Earth or what, is maybe something wrong with some of the hardware on it, And sometimes they wouldn't make bring it back to Earth. They'll just detonate something on it and it blew away and it gone into space, and all the parts scatter.
I think most of the geostationary satellites and the communication satellites, they're in low Earth orbit, so they come in contact with some air molecules. So over time, like years and years, eventually the velocity will slow down and they would fall to Earth. And I think the atmosphere is more than strong enough to break them apart before they re-enter Earth.
Yeah, they burn them up. Yeah, right. Of course, there's some of them, and so don't forget that they'll have solar panels to power whatever is on them, because they have. Remember, those are satellites that will transmit information to us, right? Yeah. So these things will go wrong and wrong and wrong. They have satellites there that are probably nearly 50 years old, right? And still going well. 100 years, wrong. You won't have 100-year-old satellite, but they're 50 is some reason, and they're there doing their work all the time, right? So the mathematics is that we just discussed, right? That force that keeps the satellite going is really the force that keeps them going is, remember, Newton gravitational force, G, okay, M, that's the mass of the satellite, the mass of the Earth over right? The distance from the center of the orb to where the satellite is, right, will be equal to mv square r, right? Because this is the force that is needed to keep the satellite going, right? To keep it going wrong in a circle all the time. So if you want to equate these two and rearrange to get v, right? You'll see that v works out to be a transposition and so on, right? G, notice, doesn't have nothing to do with the mass and so on, right? Over R, right? So depending on where you want to plant that satellite so that it will go around you, and depending on where, that will tell you at what velocity, right? You have to launch this satellite, right? And that is why they're talking when you're launching satellite, you have to produce a certain velocity that is just right, right? So depending on where you want to put the satellite, right? That R will determine that. These are all fixed figures. G is fixed. The mass of the Earth is fixed. But where you want to put the satellite, right, above the Earth, R, when you decide, okay, well, maybe you have to get government permission and so, you know, the US and Russia and so they play with their own space, right? So they have their agreement. Oh, you must put a satellite here. Let's say you have the Earth here, and my satellites must be here, and yours must be there, and all kind of craziness. I know they share orbits as well. So when they decide that now, you got to make this satellite when the satellite goes up now. You shoot it up, you shoot it up, you shoot it up. And when it reaches the position that you want it at, right? Let me say you want to launch it here. You want it to be in this orbit. You have to achieve V, right? The right V, and that V kind of puts it in orbit. And it will go wrong and wrong the Earth forever. Theoretically speaking, right? Here, my friend don't talk about air molecule and that's crazy, yeah? Right? Theoretically, it should go on and on and on because it's space. Nothing should really be holding it back. Right? So, yeah. So your V will depend on your R. Right? So this is an interesting formula that tells you, right? And the velocity that you want to launch a satellite at for it to go into a certain orbit, right? You can do a little bit of reading and so on it. Good. So let me ask a question. Let me stop this.